So hello everyone, and welcome to the September Link Tech Talk. My name is Mida. I'm the host today, and I'm a Link Frameworks project scientist at University of Pittsburgh. Link Tech Talk includes presentations and demonstrations that showcase work done by the broader Ruby software and archive community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, Tech Talks highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analysis of LST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. So today our speaker is Andy Zanidakis. He is going to talk to us about a systematic search for main sequence Dipper stars using VTF. Andy is a fourth-year astronomy PhD student at the University of Washington. His research focuses on both observational and algorithmic techniques used to discover and characterize anomalous stellar variability in large astronomy time domain surveys. He is an active member of the data commissioning and alert production team for the Rubin Observatory, evaluating time series features that will be delivered as part of LSST. He is also the director and program coordinator for the UW Planetarium. Please ask questions in Zoom or in the Link Tech Talk channel. On Zoom, you can type questions into the chat or raise your hand. As a friendly reminder, these talks are being recorded and they will be posted on the YouTube channel. With that, Andy, please take it away.
Awesome. Thank you so much, Mi, for the introduction. And thank you so much for the opportunity. Let me go ahead and hide everything here a second. Can you see that? Okay, I'm assuming that's a yes, yeah?
Yes.
Okay, awesome. All right, well, thank you so much for the opportunity to speak. Today I'm going to be talking about a project that I've been leading together with the Link Frameworks group and the UW Dirac Institute here at the University of Washington. And so we're going to be talking about main sequence Dipper stars with the Zwicky Transient Facility, but hopefully we'll get to talk a little bit also about overall doing sort of large scale searches for stellar variability in ZTF, but also hopefully in Rubin. So I think that we should start really from the back here and talk a little bit about, as we all know, once Rubin is online, we're going to be receiving this large floodgate of many stars in our own galactic backyard. And we're going to be seeing something about 17 billion stars in the era of LSST. And as we all know from previous surveys that stars exhibit many types of stellar variability. And conventionally, there is sort of a schema of how we think about the classifications of different variables. So here is just a schematic showing kind of the different classifications of different variable stars. There are some things that are extra galactic, like AGN, for example. But I want to focus here specifically on things that are stars. So what's really interesting to note about here is that this was made back in 2018. And what we've quickly realized within the last 6 years since this plot was made, that this is quickly outdated. We know of many more different types of variables that are both driven by intrinsic but also extrinsic variability. So as we're building more and more sensitive surveys that are going to be doing deeper surveys of the dynamic night sky, we're going to be, of course, discovering many new variables. So amongst these new variables, I'm going to be talking today about these main sequence Dipper stars and how this fits into this sort of discussion about classifying different sorts of things. So in order to talk about main sequence Dippers, I want to take us back a little bit and talk about how this came about. So this first originated from the Boyajian star, which was back in the Kepler Space Telescope days. So back in 2016, right around the nominal end of the Kepler survey, a citizen scientist actually had pointed out that there was a star in the Kepler survey that seemed to exhibit these really weird dips in the light curve of the Boyajian star. And Tabitha Boyajian and collaborators had led a paper and kind of characterizing what this system was. So what was really interesting about this was that now this was during the Kepler days, and so astronomers back then were dealing with light curves that were maybe 100,000 or something like that. It wasn't really a large amount of data, and so this, as I said, was spotted by citizen scientists. And so the sort of follow-up that was being done on the system was that they had found these really weird dips. And this was the first time that the community had seen anything like this, and specifically was the shapes of these dimming events, but also the amplitude of the dips. So they were too deep to be planets, and the shapes seemed to be that these were really complicated things that were occulting the star. And so in the paper, they discuss about how the different time scales of these dimming events were something between 1 and 7 days. And what was really puzzling was the fact that these didn't seem to have any repeated periodic structure. And I'll put an asterisk on that, because actually that is fairly controversial in the literature if these things are, if these dimming events are actually periodic or not. So really quickly then, others went ahead and stitched all of the photometry that was collected from Kepler, and they showed that during the 4-year mission of Kepler, actually the Boyajian star was actually showing another secular dimming event that was on top of these sort of smaller timescale things. So there were all sorts of really weird things about the system, and what was surprising is that this star was identified to be a field type F-type main sequence star, and didn't seem to have anything unusual about this. So this had sparked a huge interest in the community in trying to quickly characterize what was going on with the system. Another really interesting thing here to mention is that the Boyajian star didn't seem to have any infrared excess, which would be indicative of the fact that there might be some dust near the star. So since the discovery of the Boyajian star, there had been many papers that were trying to understand what the system was, what was causing the dimming mechanism. So there are many interesting theories, like large comets, something like a Trojan asteroid, cloud of material blocking the star. There's one theory about planet engulfment. So some planet possibly had fallen into the host star and could produce these sort of dimming events. And the takeaway from a lot of these theories is that while they could explain some of the observed quantities that we were seeing from the system, they're not all perfect, and there's still some gaps in trying to understand this. I spoke specifically about the dust, and I think this is, really interesting to talk a little bit about. So the deepest sort of a search for dust was using millimeter and submillimeter detections and trying to figure out how much dust there must be around the system to be causing these dips. So Thompson et al. Had led this search, and they tried looking for dust near the Boyajian star, and basically they hadn't found anything here. You could see in this image over here that there wasn't really any significant amounts of excess in this region. Based off of the constraints that they were able to get from the original Boyajian paper, they were able to propose some scenarios of if the material was in different sort of orbital configurations, what would be the upper limits to the amount of dust that must be there, and that would lead to an upper limit. So they concluded that the material that is around the Boyajian star can have an upper limit to about 10 to the minus 6 and to 10 to the minus 3 Earth masses, with a total dust budget of about 7.7 Earth masses within 200 AU. So it must be, very probably very few material that is near the system and relatively far away from the star, but no obvious any excess near the system. There has been some simulated work by Bodeman and Quillen, where they ran a suite of n-body simulations to see what could be causing these dimming events, and specifically smaller sort of particles or planetesimals that could be going around the star. And so what they found was that the dimmings seem to be consistent with a family of closely orbiting comets, which were most likely tidally disrupted from the primary star, and they believe that the object was something like a Sirius-sized progenitor. So this resulted to something in their simulations about 10 to the minus 7 Earth masses, which is roughly comparable to what we're finding in the observations. So this is equivalent to something like either 70 comets, which are like about 100 kilometers in diameter, or 700 comets that are at 10 kilometers in diameter. And these things most likely were tidally disrupted. However, I think that the big challenge again with this model is that there are still some dimmings within the Boyajian star that Kepler saw that these theories alone cannot explain what's going on here. So still lots of questions about this system. Now, since the discovery of the Boyajian star, there have been sporadically here and there some interesting discoveries of things that may or may not be related to the Boyajian star, and I think this is really the big question. There have been discoveries led by Assassin, by the VVV survey, and other systems, which there have been different interpretations of these sort of, dimming events of these main sequence stars. Some of the theories suggest that they could be giant impacts between planets. Others could talk about how these could be dust debris and other things that could be occulting the star. But I think what is clear from this is that there needs to be more of a systematic search in looking for these objects. Now, one thing that we have learned from looking kind of back in the literature is that these are not common events. We don't typically see main sequence stars exhibiting these sort of dimming events all the time. And we know this because of when we look at the HR diagram and we look at the fraction of variables across the HR diagram. This is from Gaia. So of course we have to put here the caveat. This is with the timescales that Gaia can observe. That in the main sequence, we typically see that stars are photometrically quiet. So we don't expect to see any sort of large scale variability as we typically see in more evolved systems. And so this is really interesting because what this is telling us is that there perhaps are systems in there where we are seeing sort of different types of variability along main sequence stars that are, something equivalent to the Boyajian star. Now, if we take one step back and we think a little bit about what kind of astrophysics are we really learning from this, we'll have to talk a little bit about stars and the environments in which they're born. So typically, the canonical view of how single solar mass stars are being formed is usually through the collapse of molecular clouds. And the clock begins at age of 0 once we have formed the first protostar. So in this stage, the star is collapsing under the Kelvin-Helmholtz timescale. And in this phase, the protostar is mostly dominated by accretion, outflows, winds, and has a very thick, opaque envelope. And so at this phase of the star, the star is barely visible even in the infrared. So here I'm putting a little indication of how much infrared excess is there in the system. And so in the protostar phase, we could barely see them in the optical. So you usually need infrared surveys to do this. So this is within less than 1 million years of when the star has just formed. And then we approach the pre-main sequence phase. So this is within right after the 1 million year mark, where we're still being dominated by this gravitational contraction and some deuterium fusion begins to kick in. But even in this phase, stars are exhibiting all sorts of different complex stellar variability that is mostly driven by accretion, winds. The stars are actually rapidly rotating, so there'll be all sorts of really complicated stellar variability that we typically see. And then after that, the 10 million year mark, where the star should be finally arriving on the main sequence, where we begin to see hydrogen fusion. This is where I think there's a lot of interesting work that needs to be done in trying to understand this transition between the pre-main sequence to the main sequence, and then how does that ultimately lead to planet demographics. So after this 10 million year mark, we think where debris disks are beginning to form and planet formation begins to being formed. These are kind of the stages where we need to be thinking carefully about on how this leads to the current exoplanet demographics, but also how does it go between these transitions between the pre-main sequence and the main sequence phase of material. So one thing to talk a little bit about, in case folks are not familiar with, is how exactly do we expect planet formation channels to occur? So the classical theory tells us that planet formation usually occurs through the collision of what we call planetary embryos. So once the material around the star has coalesced and material begins to clump together, these embryos will begin to bump into each other. And depending on the kinematics and the dynamics of that disk and those embryos, they will undergo these collisions and will go oligarchic growth. And so these smaller pieces will bump in, will become bigger, and then those bigger pieces will bump into other pieces. So it's kind of like a cascade of different collisions. And at one phase, once the material is big enough, the planetesimals are big enough, you'll begin to get these events called giant impacts. So basically, these could be objects that are like maybe the size of like Mars, for example, running into other planets. And giant impacts are really important, as we know in our own solar system, that formed, for example, the moon. And depending on different flavors of giant impacts and, kind of the physics that's being driven here, this can change a lot about, tell us a lot about the different demographics of planets that we see in our own solar system and possibly even moons. And so while in the community, there's an agreement that giant impacts do occur on other stars, that the frequency at which they occur is a big mystery. And that can help us inform us on, how planets are being formed and et cetera. So within the community, there has been views of these giant impacts, we believe. So back in the era when we had Spitzer, we knew about a few systems that had extreme infrared excess, and some spectra had shown that for a particular system where if you look at the spectrum, they were mostly dominated by amorphous silica, which is consistent with if you take two rocky worlds and you smash them together under immense heat, and you will begin to see all sorts of interesting spectroscopic features that are consistent with silica. And more relevant to sort of the time domain discussion with, especially with LSST, is that some of these giant impacts are believed to even cause transients. So specifically in the infrared, if the collisions are close enough, we could see either infrared excess, so specifically in the near infrared, and also there's been some reports about X-ray transients as well that could be producing these. So these giant impacts that are occurring could tell us a lot about these systems. And there's a really nice intersection here of using time domain surveys to go after these interesting systems. Now, I wanted to put this all together and talk a little bit about sort of the different timescales and durations, the timescales and depths that we're seeing of these objects. So here I'm just showing the relative depth and timescales of some of these main sequence Dipper stars. And you could see that only a handful of systems have been discovered that have these sort of longer timescales, whereas Kepler and other surveys had already discovered things that are are happening much faster. But what we do know for a fact is that most of these systems are very rare and they're stochastic. And so this is kind of a perfect opportunity for us to kind of go after these before Rubin comes online. So there have been previous searches been done before for these main sequence Dipper stars, going back, of course, to the original Boyajian et al. Paper, where they had basically noted that there were no neighboring sources that had exhibited this sort of type of stellar variability. There was a quick note by Dara Lacourse, who had shown that basically they visually inspected most of the K2 stars. So it was about 165,000 stars, and they found no Boyajian star analogs. But the first serious search besides Kepler was done with the Northern Sky Variable Survey, where they looked for basically through 2.5 million stars. And this was a blind search. So basically taking all stars in the Northern Sky Variable Survey and looking for these so-called main sequence Dipper stars. And what they found was they basically 21 Dipper candidates, and about 10 of those were on the main sequence. And one of the key findings that they suggested was that these are actually on bimodal timescales. So they're things that are happening really fast, that are days, and there's other things that are happening on longer timescales, such as weeks and months. Now, one thing that I said about this is that this was a blind search. And this is actually quite complicated because of this diagram over here. So here, what I'm showing is the time scale of stellar variability for things that are commonly what we call dippers. So that exhibit these sort of stochastic dimming events. And this is, just roughly proportional to, the amplitude, which is basically telling us how deep those dimming events are. Now, I want to point out, where exoplanets are, these are tiny little transits that are happening on the timescale of just, a few hours. But in reality, when we're looking at the sensitivity of what we can probe with with ZTF and with Rubin, right, we're going to be looking at things that are relatively large amplitude dimming events, and the timescales are going to be going, between something like days to years and to a whole decade, really. And when you really look at this diagram, you can see that there's a lot of complicated things going on that also exhibit these sort of dimming events. So a blind search is really difficult to discern between, young stars, Arcor borealis stars, or all other stuff that might be as contaminants to the system. And so we really need further context to really make a claim if these are, main sequence dipper stars, such as like the Voyagian star and other systems. We really need to know more information about the system. So this is where our work has come into play, where we wanted to do the first systematic search for these main sequence dipper stars. So what we did is that we're selecting a very specific region on the HR diagram where we're looking only for F, G, and K dwarf stars. So these are roughly solar analogs. And we're combining the power of the Zwicky Transient Facility to look at the light curves and using Gaia to inform us about the distances and other stellar parameters that we need to assess these stars. So the initial sample was something about 100 million stars. And once we do the cross match between ZTF and we remove most of the spurious photometry needed, we result in something about 63 million stars, which is equivalent to about 126 million GNR light curves. So this is roughly the data size that we're working with. Now, the way this search was being done is relatively straightforward in the sense that we want to look at the full archival ZTF photometry. We want to compute many time series features, and then we would basically derive some sort of metric that would tell us the outliers that are present in a light curve. We would identify those, and then we would fit them using a Gaussian, and then assign a score to each light curve that would tell us basically the strength of a dipper if it's present in the light curve. So really, in reality, what we're doing is that we're computing a bunch of time series features for all of these stars. Now, I want to talk a little bit about the technical side, and so this was done in collaboration with the LINKS frameworks group, and specifically, this project was exploring and using two specific tools, the LSDB and the Nested Pandas frameworks of how we could do this sort of analysis. So for LSDB, right, we're using this package as for cross-matching, which is basically doing a hierarchical sky pixel partitioning, where we're taking all these different surveys that we have, like ZTF and Gaia, and we are basically performing cross matches. And what's really awesome about LSDB is that it allows us to do this really fast, and it allows us to access the data really, really quickly, but also to do the sort of fast cross matches between the different catalogs that we're using. And then the second tool was Nested Pandas, which basically is the pandas data frames that are nested within each other, and we could treat now each row, and it will have an attribute of the time series data that we're dealing with. And so together with these two tools, we can basically do the sort of analysis that we're recommending. So I recommend that you all go check out the docs page for both of these tools, and feel free to ask me questions after this presentation or on Slack, and I'll be happy to talk to you more about these tools. But it's been really awesome to work with the Link engineers and thinking a little bit about sort of the use cases that we need to have these tools, and kind of doing these sort of searches for stellar variability. Here is just showing you a flow chart of how exactly the sort of analysis works. So, in reality, you could work with an N number of catalogs that you can cross match. So you usually bring this into LSDB. where you will hipscat them, and then you could perform quick cross matches, and you could do various different kinds of queries to your different catalogs, both the object catalog, but also the source catalog as well. And then where nested pandas comes into play is where we could take then the source catalogs and object catalogs, and we can combine them into one. And what's really awesome is that because this is highly modular, we can fit in our own customizable Python time series evaluation routines or pipelines and things like that. And in the backend, we're using Dask to parallelize this process. And this is all being done lazily. And so this is a really friendly way of working with really large data sets and not having to bring everything into memory. And I think that this is, for me personally, this has been a really growing experience in learning how to use Dask and trying to work with things in lazily instead of bringing enormous data frames into memory and struggling a lot sometimes with performance. So the nested pandas I think is really promising, and here I'm just showing a quick demo of where in reality you could really do n numbers of layers of nested pandas data frames within your master data frame, where you've collected information both on the object level catalog, but also you can feed in different time series informations. So here we had shown that you could do this, for example, and feed in here we did for 3 different surveys. So this was with pan-stars, ZTF, and the unwise data. And I think this is very powerful in how we think about doing stellar variability searches in the era of LSST, when we might have data from LSST and Euclid or Roman, for example. And so this is really awesome in being able to do both simultaneous pipelines that will incorporate multi-wavelength investigations instead of working with just one source catalog. So here we had just tested what this would look like, and we were able to recover a known dimming system that we had written a paper about last year. So next steps for me personally, I think that I'd be really curious to explore what this would look like in a more scalable way. So, trying to do multi-wavelength Dipper searches with different surveys and trying to assess the performance between, nesting it once with only just one source catalog versus, maybe three source catalogs, for example. This is just showing here that, these are kind of signals that we might be able to go after, where you might be seeing infrared transients, but also they would be optically dimming in the optical wavelengths. And so this would be empowered through those tools. Now, I wanted to put this slide over here, and I believe Nevin and Doug Brenton have given a previous link tech talk before on LSDB and nested pandas. So I put a QR code here if you're interested in going to see their talks. But I just quickly wanted to discuss a little bit about some of the things that we've learned from this workflow and some of the current challenges. But I think that the key advantages that we're seeing with this current workflow is, of course, that the inherent pandas data frames is, I think, very easy to use. And this makes it very easy to the learning curve of how to take these tools and scale it to your workflow. I think is very easy, especially if you're already familiar with pandas. Another really awesome thing is that these workflows are relatively flexible for both small and large scale data analysis. And maybe I should put an asterisk around the large, because we're currently trying to understand just how large these workflows enables us to basically do these sorts of stuff. But I think it's very important to mention that this also enables us to do smaller analyses. So let's say, in the era of LSST, something small might be like, let's say, 1 million stars. And so having tools that allows us to go between something that would be like either a few thousand stars or a few million stars, I think is very important. And the ultimate goal, of course, is to be able to do something like the whole ZTF object catalog, which might be, let's say, like 1 billion objects or so. And then finally, I personally have been enjoying really the Dask dashboard GUI, which is very helpful in trying to optimize, different codes that are the modular pieces that I've been adding into these pipelines, and in trying to inspect the performance and understanding really where are some parts to the code that we can optimize. Some challenges I think that have already been mentioned in previous tech talks, as I said, are specifically, I think the most important one is the memory management issues. Now, I'll highlight over here that in previous versions of what we were calling tape, where it was treating the object and source tables as separate, whereas now Nested Pandas has combined them, we're still seeing some memory management issues, not as much as we typically would see with tape. And basically what this issue is telling us is that Dask is not really good at trying to sort of manage the memory that it's bringing in. And a lot of times the workers that you are assigning to a large computational task might, for example, die because there are memory leaks happening all the time. And this could be very frustrating in trying to figure out where exactly are these bottlenecks in memory. Other things that I experienced was like slowdowns with large task graphs for really large queries, for example. So there could be a really large overhead of a query where you won't even run your computation until Dask, for example, has formed its task graph. And so one thing that we did find is that if you were to actually break it down a little bit more, the queries, that this would sometimes speed up things significantly a little bit faster. And then, you know, some other things that been pretty interesting is we need to be careful, you know, like how we do these sort of large operations, and you know what things are we bringing into memory. Of course, this implies basically that we need to be more smart on, you know, the kind of queries that we're doing to our time series analyses and things like that. But overall, I think it's been a really fun experience in working with these tools, and it's been very helpful. And you know, I'm very appreciative of the Link engineers that have been really supportive with this project and have basically allowed us to do this sort of analysis. So one thing that I wanted to talk about here was, so, you know, I said that we want tools that are both flexible for small and large scale analysis. And this was exactly the case for when we first started this project, when we were looking for initial prototypes of our algorithm to identify these dippers. So here what I'm showing is the sky distribution of the identified dipper stars. And we've basically selected all stars, and they're color-coded by the time at which the highest amplitude dips are occurring. And what I want you to take away from this diagram is that you can see that there's a bunch of structure in the sky. And this was something kind of unexpected. And what we learned from this is that our searching pipeline was actually very sensitive to a lot of the systematic errors that are present in the ZTF data. And so what this requires is to do several iterations of, you know, trying some sort of pipeline, running it through, you know, a few million stars and trying to assess, like, you know, are we avoiding most of these systematic effects or not? And so that's why I think it's important to have these tools where you can go back and forth between, you know, smaller analyses to bigger analyses, where we could do something like, you know, 63 million stars. And so we were able to remove most of these systematics by specifically looking at the time at where these dippers would occur. So here I'm just showing the time at which the dip occurs and the number of dippers. And you could see that they actually occur on very specific nights, that is telling us, you know, that could have been like specifically like a bad night. Something could have been going on, let's say maybe like clouds or something like that. It could also be pointing out to like maybe some calibration issues as well. But so we basically went through these aliasing times and we removed all times to basically remove most of those systematics. And so here you could see the before and after with the systematics and then without the systematics. We get a more uniform distribution of stars. So we believe that this sample is then mostly free of systematics. Here I just had a slide about talking a little bit about what kinds of systematics we're seeing. So the most common ones are mostly CCD edges. So if a star is going in between and out of the CCD edge, it could create these, you know, fairly convincing dipper-like events that our pipeline was picking up. And then other things like, you know, bad columns. If the star is going between the bad columns, it can also create these sort of dip-like events. So talking a little bit about the outputs of this project, we've been able successfully to find, I think it's about 80 or so of these dipper candidates. And we've been able to put them on the HR diagram to confirm that they are indeed F, G, and K type main sequence stars. And there's a variety of different sort of phenomenology that we're seeing from these light curves. And this is just an ongoing task now to trying to understand the sort of broader context of what these Dipper stars are. Here, I'm just showing you the scores and features that we've been able to compute from some of these, from all of these Dipper stars. And here's just looking at the distribution of the score. Now, as I said, because we're dominated so much by systematics, the way we are been identifying them is by doing injection and recovery simulations using the same workflow. So the nested pandas, the same workflow to kind of do sort of simulations of, if we were to take a simulated Dipper star and try to see where the score would be based off of the simulated light curves, then we could set, cutoff points to where exactly we should be looking for these Dipper stars. And so we believe our pipeline is complete to about 90% for finding, a single dimming events. But, in reality, there are some stars that might have multiple dimming events that may or may not be periodic that we also need to investigate. Here, I'm just showing, I know that I talk a little bit about the ZTF systematics and that might worry some, but we were able to confirm all of these Dipper stars independently using URSA, and where we were able to remove some of the bad photometry that unfortunately is not possible through the bulk photometry releases, the catalogs of ZTF. And so here I'm just showing, the one specific Dipper that we found, and I'm showing you here what the light curves look like for different neighboring stars to be more convincing that these are actual bona fide dimming events that we're finding. So you all might have the question now, okay, so what are these really these mysterious main sequence Dipper stars? And as I said at the beginning, there are many stars that have very similar types of stellar variability that we need to be careful in before we make a claim that these are actual Dipper stars. And specifically, young stellar objects are very common and have very similar sort of dimming events. And so here, what we've been doing is we've been looking at the near-infrared colors of these main sequence Dipper stars. So in black are the stars that we identified. And I'm plotting here different types of young stellar objects. And you could see that most of our sample is systematically bluer than most of the other known young stellar objects, except for these weak T-Tauri line stars, which there seems to be some overlap in color. And the only way to discern between these two different populations is actually through spectroscopy. We need to look at the spectra to make more robust classifications. Or if you're lucky, if you have deeper infrared colors. So I think that in reality, what we need is deeper infrared colors, specifically in the W3 and W4 colors. But unfortunately, for most of our sample, we don't have those because there's non-detections there that we've looked. So next steps should include to look at the spectra of some of these objects. Another game that we could play is start to begin to make some statements about sort of the broader sort of population of these main sequence Dipper stars. So because these are cross-matched from Gaia, we have the distances. Although for most of these, we don't have exactly we have the proper motions, but not the radial velocities. And so we cannot make the full 6D assessment of these stars, but we could look at specifically at the galactic scale height. And what we could see is that there seems to be some agreement with the thin disk of the Milky Way, but thereafter, at one point, there seems to be this factor over here, this region over here, where it seems to deviate away from the thin disk. And so really what this is pointing to is perhaps a preliminary suggestion, and I'll put an asterisk here that this is still a work in progress, that we're still trying to understand if these are, slightly older stars or if they're younger stars. And so the idea here is to begin to characterize and trying to figure out, okay, are these young or old stars? Because that will tell us a lot about, at what phase are we catching these stars and why then the dimming events are occurring. As I said, we need spectroscopy, and we have already begun to do that. So here we have just two spectra of two main sequence Dipper stars. that were collected for us. And we could see that there's really no peculiar spectroscopic features in these spectra, which is kind of what we were anticipating and what is in line with previous findings from other main sequence Dipper stars. But as I said in the previous slide, we really need to have the whole sample here in order to make some concrete claims that these are true main sequence Dipper stars. And ideally, we want to look at metallicities and the radial velocities and kind of tie that all in together with our sample. So this upcoming quarter and the next year, we're going to be trying to run a relatively large spectroscopic campaign to get spectra of all of these systems and try to do further characterization. This is a fun figure that is very new. So again, please be aware that this is work that in progress. But it turns out that if you make a really naive assumption about the material that is occulting the star, if you assume that it's on a circular orbit and that it is completely opaque, that you can derive basically a lower limit to the transiting velocity of a system and the upper limit to basically the semi-major axis based off of just the gradient of the flux that you're observing from the system. And of course, this is dependent on knowing the mass and the radius of the star at play. And so these parameters we get from Gaia, and the change in flux that we're seeing here, this is basically telling us how fast the dimming events are happening. And so this will tell us basically the scenario for the semi-major axis of circular orbits. And again, this is an upper limit. And what we find is that the upper limits usually lie around somewhere between about 10 to 100 AU, roughly where we think most debris disks are around in that region. And again, this is kind of a step in the direction where we're trying to constrain something about where exactly are these dimming events happening with respect to the star. And also, again, the big mystery of why aren't we seeing any obvious infrared excess if this is a lot of material that is going around the star. So here again, I've just plotted the time scale versus depth of most of these main sequence stars and with respect to other known Dipper stars. And so you can see that we've started to begin to fill out this sort of longer time scale phase space. And of course, once Rubin will be online, we'll be able to extend this even further and hopefully probe a much larger volume. But this program has proven to be that we've been able to successfully define at least 80 of these Dipper candidate stars that we need to do more classification. And as we start to begin to think about what this search will look like in the era of LSST, here was this really fun plot that I had made last year in showing what a sporadic Dipper would look like with Rubin data, with simulated Rubin data. And you can see that it is possible, things that are, relatively long time scales, and we're able to, recover what these dimming events would look like. So what would be awesome is to envision a future where we could, do some sort of multi-messenger TOO synergies where we could catch these dimming events happening in real time and characterize them as they're going through the dimming event, because outside of the dimming event, these stars seem to be relatively normal. And so the tools that we've discussed here really are empowering us to think about what comes next for LSST and future releases of Gaia and Roman and all sorts of exciting surveys that are coming online. And these tools have really been an awesome step in doing these sort of analyses. Okay, so I will leave my conclusion slides here. And again, I want to give a special thanks to Nevin, Doug, and Wilson and the Link Frameworks group for helping me and with these tools. And yeah, I'll be happy to take any questions. And thank you.
Okay, thanks, Andy, for the excellent talk. We have some time for questions. If there's any from the audience, please raise your hand or unmute yourself. Okay, I'll ask one first. I'm curious if you have done any study on how the cadence of LSST would change your search results.
Yeah, so one really big issue is that we don't really have a model for what these dimming events look like. So in this case here, I just simulated like a skewed Gaussian would look like. But if we look back a little bit at the light curves, you could see that there's all sorts of shapes and different sort of dimming profiles that we're seeing. So I think that it's most likely that Rubin will probably be more sensitive to the longer timescale things than what like TESS like TESS or like Roman, for example, would be able to see. So I think that like a really cool synergy will be like between like Roman and LSST, for example, where Roman will have higher cadence, and Rubin will be able to be more sensitive towards the sort of longer timescale things. But one thing that we're hoping to get out of this study is that to kind of get a sort of average model of like what most of these dimming events look like. Are they all Gaussian? What are their sort of characteristic timescales and things like that. So not yet, but hopefully we'll be able to run some simulations before LSST turns online.
Thank you. Okay, if there's no more questions, or if you have more questions, you can send your questions on Slack after this talk also, or to Andy directly. Okay, if no more questions, thanks Andy again for his excellent talk, and thanks everyone for attending the Tech Talk. So the next Tech Talk will be on October the 10th at 10 a.m. Pacific. We'll be hearing from Emilio Di Noso about a 2-point correlation function on LSST scale. It's one of the Link incubator programs that is recently completed. Please join the LSST Link Tech Talk channel and the link at list.lsst.org mailing list for more information and future announcements. With the speaker's permission, we'll post this Tech Talk on our YouTube channel within the next few days. Thanks for your attending.
Thank you so much.